This is UKMT Junior Math Challenge from 2019. 5 points for the first 15, 6 points thereafter. You don't lose any points for getting anything wrong, so you may as well just guess every question if you're unsure. But anyway, let's make a start then. So, okay, we'll do 25 minutes until midnight, just being 35 past. Then there's an hour or 60 minutes until 1 a.m. and then another 15 minutes to go, and you put it all together and you get 100 minutes in total. Excellent, so nice start there. Here, just make sure you do the brackets first. Doesn't really matter whether you do adding or subtracting first. Just work left to right is probably always the best shout. So putting those two together, or I think actually all of these together, we're going to get 0.6, 0.3 from those two, and then another 0.3 is 0.6. Minus 0.4 is 0.2. And now to do this, when you're dividing, you're allowed to just times both numbers by the same thing. So I can times both these numbers by 10, and this result will be the same as this result. It's just a nice little trick there if you're dividing by decimals. And then if you want to, you could do a bus stop and do 2 divided by 5 and just check out what decimal it is. If you don't recognize this is the decimal of 0.4, which it is. Alternatively, at this point, dividing by 0.5 is the same as timesing by 2, and 0.2 times by 2 is 0.4. However you want to do that, that's just going to be the answer there. 3. Sam has eaten 3/4 of some grapes, which means that he hasn't eaten 1/4. So as the ratio eaten to not eaten, or actually not eaten to eaten, is 1/4 to 3/4. And now this isn't any of the answers, obviously. And in case it's obvious to you that we can just times by 4, that's good. If it's not, just grab a completely other random ratio here. We're allowed to, of course, divide this ratio by the same number, right? So divide both things by 5, you get 3 to 4. But you're also allowed to multiply. Multiply them both by 2 and you get 6 to 8. So here we can just take that idea and we can just multiply both sides by 4. You're allowed to multiply or divide by the same number. Multiply both by 4 and you get 1 to 3. Cool. Question number 4. 1 to 3. Question number 4. I can't really explain how I did this so easily. I just looked at these shapes, tried to find one that I could break into 4 pieces using a single cut, and it was fairly obvious to me that I could just do this to make 1 piece here and then 3 more pieces here, and that would be my answer. I don't know whether it took other people a little bit longer to get that, I'm not sure, but I just did it very quickly like that. So I just wanted a quick drink of water. Question number 5. On this person's birthday, I'm not going to pretend to pronounce that name, Buster, whose name I can pronounce, was 3 times her age. So 3 times 16 means Buster was 48 at this time. On this person's 21st birthday, well, that's 5 years later, right? How old was Buster? We'll just add 5 to this number, and you're going to get this answer here. Question 6, which of these is closest to 7? Well, just look for the difference between the number and 7. So the difference between this and 7 is 0.09, and we're looking for the smallest difference, or distance. The distance here is 0.082. I think if you do a column and take these away, do a 7.000 and take away, you're going to get this. The distance here is obviously 0.17, distance here is obviously 0.3, and then distance here is 0.085. Now, you're looking for the smallest distance, and the smallest distance, obviously not going to be these because they have a 1 in the 10th digit. It's actually going to be this one. It's going to be the smallest, slightly smaller than that one, and this one too, so it's going to be B as the closest. So the shortest street in the UK is 2.06 meters long. Longest road is 7,821 kilometers. How many times longer? So you need to times this road by some number to get this road. So 7821 equals 2.06 times some number. And we're looking for what this number is. Except a couple of things to do here. Firstly, these units are wrong. So to put them both in meters, I'll keep this one as meters. To put this in meters, I need 7,821,000. That'll put it in meters. And also approximately, right? So let's just not deal with this. Let's make this a 2 and make this an 8 million. And now, of course, 2 times 4 million is 8 million. So we're going to get an answer of 4 million times longer. Good. Question 8. So we've got a kite inside of a rhombus, which is interesting. So this is a kite, and then we've got a rhombus. What's the size of angle FPG? So we're looking for this angle here. Okay, cool. So the first thing I can do is, well, these 2 triangles up here, I know 2 of the angles, so I can work out the third. 180 minus the other 2 gives me this angle is 25, and likewise this one is also 25. Now I think that actually the key piece of information here is that we've got a rhombus, S or PQRS. And now rhombuses have opposite angles the same. So we can see 120 and 120 is the same here and here, so that's good. But also these angles need to be the same. And now there are 360 degrees in any quadrilateral, so 360 take away 120, take away 120 is 120. And then that needs to be shared equally between these two angles. They're going to be 60 and 60, which means looking back here, this whole angle must be 60 because this rhombus is just this whole picture minimalized a little bit. So this whole angle must be 60. So we just do 60, take away 25, take away 25, and we get the answer of 10, I believe. Number 9, this is just a fabulous question, and there's a very hard way of doing it and a very easy one. Something that I teach every single class that I've ever taught percentages to is x% of y is equal to y% of x. In other words, you can just swap the percentage and the number, and the answer is always the same. I'll leave it to you to verify this using some of these examples if you want to, or to prove it yourself if you have some time. I'm not going to bother here. But you're allowed to just swap the percentage and the number over. Trust me, it works perfectly well. Something you probably want to know going into a math challenge. Because of course this is nice, 50% of 18.3, and this isn't. So let's just swap these two around and make the question, what is 50% of 18.3 plus 50% of 18.3? And now I could halve 18.3 to find it, and then put it together with another half. But actually, if you're just doing 50% plus 50%, that's going to be 100%. And 100% is just the number. So the answer is just the number 18.3. So lovely question there. No maths required, just knowledge of this thing instead. Question number 10. What's the last digit of the smallest positive integer whose digits add to this? Okay, so now let's think about some integers here. And let's think about a simpler case. Let's think about digits whose sum to 11, so a much smaller number than this. Here are a bunch of numbers whose digits add to 11. And think about which is the smallest and why. What rules can you come up with for making a number as small as possible whilst the digits add to some other number? Okay, so we want as few digits as possible is hopefully one thing you thought, right? This number is smaller than this one simply because there are fewer digits. We also want to put, and therefore that means we want to put 9s in it. Like having 9s is great because it lessens the other numbers that need to happen, and therefore shortens the number down. So we want 9s, even though 9 is a big number, but we want them to shorten the number itself. And also we want to put the smaller numbers at the front. Right. So once you've got a bunch of 9s, if there are numbers that aren't going to be 9, they need to be at the front. Right. That's why this number is smaller than this one. So okay, what we're going to do is we're going to say, to make a number have this digit sum, we're going to slam a bunch of 9s in there, and then whatever remainder is needed to get up to this, in case this isn't a multiple of 9, we'll just put that number at the front. Now, having said that, you probably can figure out the answer to this question straight away. If not, I'll just do it more clearly to show you. But let's see how many 9s fit into the digit sum in total. So do a bus stop, and you'll find that there are going to be 224 9s with 3 left over. Which means for a number to have a digit sum of this, digit sum means the sum of the digits, I need to have 224 9s in the number with some number 3 as well. And so the smallest number is going to be this. Now there are other things that could do it, of course. I could put a 1, 1, 1 at the front, but that makes the number longer, and I don't want that. I want the number to be as small as possible, as short as possible. So I'm going to put a 3 here, and it needs to go at the front because, of course, the smallest digit is at the front. Which of course means that the last digit must be a 9. And so this was kind of unnecessary based on previously what I said here. You can tell the 9 needs to go at the back because there's just going to be a bunch of 9s and then something else. I didn't need to work out what this was, but it's nice to know that this is the number, actually. Anyway, the answer is 9. Question number 11. I'm not really sure how to demonstrate how to do this question. It's kind of a weird one. There's a game. They take it in turns. You need to write a number that doesn't already connect to another number. So for example, the next player can't put a 1 here because it already connects to a 1, so a 3 has to go here, for instance, because you can't put a 2 here and you can't put a 1 here. And then whoever loses is the person who can't put a number down. So here, for example, it's our turn. So if we put, say, a 3 down here, the other player is fine because they can just put a 3 here and the game is a draw because this doesn't connect to any 3, so that's fine. Likewise here, we could just put a 3 down here, and the other player could just put a 2 here because it doesn't connect to any. But also we could have put a 3 here and the other player could put a 2 there. We could have put a 2 here and the other player could put a 3 there. So there's nothing we can do. That's just going to be a draw. Likewise, this is going to be a draw as well. You put a 3 here, other player can put a 2 there. Even if you put a 2 here, the other player puts a 3 here. Like, it's just a draw. You could even put a 1 here. The other player could just put a 2 there. It's fine. This is the one that's a bit different though, because we think here actually, if we put a 3 here, here, the other player has to put a number here, but can't put a 3, 1, or 2 here, and that's the only numbers they're allowed. So this is a winning game for us. Don't need to check this one because it only says in which of these, so it must be one of them. So yeah, that's the winning one. 12, Jamal writes down a sequence of 6 integers. He uses the rule after the first 3 terms, so this doesn't count the first 3 terms, but after the first 3 terms, each term is the sum of the previous 3. So it's kind of like a Fibonacci, but a sum of the previous 3. So if we call these terms A, B, C, A, B, C, clearly A plus B plus C is 8, because that's the rule here. But also, that continues, right? So B plus C plus 8 is 13. And also, C plus 8 plus 13 is 25. Now here I just rearrange this a little bit first, but then we can look at C plus 8 plus 13 is 25. Again, take away, add 8 and 13 first, I guess, then take away, and we get C is 4. If you know C is 4, this gives you that B is 1, and if you know C is 4 and B is 1, that gives you that A is 3. And we get our first term being 3. Excellent. Question number 13, so we're going to draw some lines to make the spelling JMC. So we're going to start at the J and go outwards. Now there are 8 places to go from the J, either there, or there. And now, okay, so you've got 8 choices for the first kind of bit that you do. And then from here you've got, well, it actually depends where you are. If you're on one of these M's in the corners, you actually have 5 C's to go to, any of those 5. Now if you instead, and that would be the same here, right, 5 choices here as well. But if you instead go to one of the middle M's, you only have 3 choices to go to. So we can just add these up in turn. So if we go here, there are 5 choices, plus the 3 choices here, plus the 5 choices there, plus 3 here, 5 there, and so on. We just add all those options, and we get 32 in total. Question number, 14. So, okay, we have to travel along here. We're not allowed to repeat a vertex. So what I take that to mean is you can't do this, this, and then go all the way around and then go across here. Even though you haven't used a side twice, you've used this vertex a couple of times because you went through it here, you've gone through it now, and you can't go through it again. So you're not allowed to repeat a vertex, it says, which is a fancy word for a corner, which of course means you're not allowed to use an edge either, because that would require going to the same thing. Now it made sense to me to start here, because if I don't start here, there's no way of me using this bit here, because I can't go around out to it, because then I have to stop. So it made sense for me to start here and then maybe go the long way around this this shape here, like this. So that's, well, so far I've got 1, 2, 3, 4, 5. Now I could go out from this triangle, but as I've said, I'm currently sitting on this vertex, this corner here, and so I can't actually go around and continue, because then I'll be using the vertex twice. So actually it seems to make more sense, if I want the longest road, to go around the square, not the triangle. So I'll go this way instead, like this, and then that's as far as I can go, right? Because I can't go in here because I've already used this corner. I went through it like this, so I can't go back to it. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And actually, I think I probably would have got this question wrong if I was taking this under time pressure, because I probably would have just done that and been happy with it and moved on. However, if you think about it for a little bit longer, and I only thought about it for longer because I had to spend time animating these arrows in, which was very boring. If you think about it for a little longer, actually starting here is not optimum, because you only get 1 free movement here, 1 arrow. If you start in the triangle, which otherwise goes wasted, you can actually get 2 free arrows by going around like that. So let's instead start up here and do that. And now I get 2 movements before even hitting this hexagon here. So that's cool. Now I can go around it the other way maybe, ignore this line because I don't need it, and then go around the square. And you actually get 1 extra length, and so you end up going 10 in total. So quite a nice question there, required a little bit of thought, but sure. 15, so we've got these 4 arrow shapes, and we need to cover this shape with no overlap perfectly. So let's just put this first one here with the dot there, and then we can put the other ones around like this. And that tells us that the dot can go in this corner here, right? Clearly, because I've got a solution. The question is, by the way, how many different places can this dot go? So it could go in all 4 corners, of course, because I could just rotate this box around. Like I found the solution that puts it there, but of course I could just rotate the entire solution to put the dot up there or there or there. So it can go in all 4 corners just by a bit of rotation. But also looking at this, I didn't have to choose this one here to be the one with the dot. I could have chosen this one to be the one with the dot. So actually I can go here as well. But I can also go here for the same logic, right? Because I could have just put the dot in this one. But also, again, doing a bit of rotating, if I rotated this 90 clockwise, I'll get this solution. So the dot can also get there, and likewise, I could have rotated this one 90 clockwise to get the dot down there. and by a bit of reflecting, if you reflect this maybe in a mirror here, you can get the dot there, and likewise the dot here could have gone to the dot there. So I can get all of the edges just by a bit of rotating, bit of reflecting, bit of trickery, but I can get all of the edges here. So if you need to spend a bit more time thinking about how and drawing that out to reflect and rotate it a bit to get all these, do so. But I'm happy with that. I can get all of these. Now I just need to think, can I get the middle dots? So the first thing I thought was, okay, what if I put it in like this? Well, there's a problem here, which is that this line here, I don't think I can fill in because my L shape's only a 3 long, right? So I can't really fill in all of these 3s. I could fill in like this bit, but that would leave one over here. Or I could do this bit and that would leave this one. So there's not much I can do here. So this seems like a bust. But what if I instead did it like this? Because now I think I can get one over here, one there, and one there, and that works perfectly. And so I can definitely get the dot here, but also I could have just put the dot here, here, or here, so that actually satisfies all of them. So I think I can get them in all of the dots, in all the squares, all 16. So quite a nice little question. Again, required just a bit of thought and playing around with, I think, to get it right. But anyway, number 15, Tasman write down 3 2-digit integers. One is square, so let's list out the squares that are 2 digits. There they are. One is prime. Now, I actually don't know all of the primes off the top of my head up to 100. It would require quite a lot of me thinking to do that, and I don't really have time for that, so I'm not going to bother with that. Triangulars I do know. In case you don't know what a triangular number is, it's, I mean, there are some nice videos on YouTube about it. They make triangles, essentially, just like the squares make squares. A short way to remember them is that you just add 2, then 3, then 4, then 5. You add 1 more every time you go along. So that's how I generated this list, because I actually don't know these ones off the top of my head. I just added 1 more than I did before to get the entire sequence. Of course, this bit doesn't matter because these aren't 2-digit, but I just wanted to start there anyway. And now we're only going to be using these digits, and we're going to use them exactly once. So I don't have a 1 or a 2 or a 9. So let's just cross out, or a 0. So let's just cross out everything that has a 1, 2, 9 or 0 in it, because those clearly aren't the numbers she's writing down. So crossing out all these, still crossing out. We're not left with that many, actually. Now we can't write 36 as our square and 36 as our triangular, because we're using all the numbers exactly once. So let's figure out what pairs can go together here. The 36 can go with the 45 because they don't share any digits. So she could have written down 36 and 45 as a square and triangular. We'll think about the prime number that she wrote down later. 36 could also go with 78. And 64 can go with 78 as well. Can't go with 45 because of the 4, can't go with 36 because of the 6. So these are the 3 pairs that she could have written down. Now, what numbers or what digits has she not used for each of these pairs? Well, here she hasn't used the digits 7, 8. Here she hasn't used 4 and 5, and here she hasn't used 3 and 5. Okay, so what primes, 2-digit primes, could I possibly make out of these two? Well, I can either make 78 or 87. Now, clearly 78 isn't prime because it's even. I actually don't know about 87 off the top of my head. However, it's not one of the answers, so either it's not prime or it doesn't matter because it's not the answer anyway. Turns out it's not prime. It's divisible by 3 because the digits added up to 15, but I didn't think of that at the time. So here I can either make 45 or 54. Clearly neither of these are prime. This is even, and this is a multiple of 5, so not prime. So this can't be the setup. Here she can make 35 or 53. Now 35 isn't prime, but 53 probably is, and actually it definitely is because it's the answer. So as soon as I found that one, I knew I had the answer there. So she did this. She wrote 64, 78, and 53 down, and that's what she did. Number 17, a rectangle is 3 times as long as it is high. So here we're going to do a classic Mr. Drew strat, which is, okay, they haven't told me exactly what this rectangle is. I'm going to make it up. Here's a rectangle that's 3 times as long as it is high. Good, okay. The area of a square is 12 times the other rectangle. Now the area of this rectangle is clearly 3. So the area of this square clearly needs to be 36, which means its sides need to be 6, because 6 times 6 is 36. What's the ratio of perimeter of the square to the perimeter of the rectangle? Now the perimeter of the rectangle is 1 plus 3 plus 1 plus 3, which is 8, and the square is 6 plus 6 plus 6 plus 6, which is 24. Square to rectangle is 24 to 8. Simplified down is 3 to 1, and that'll be my answer. Making up numbers when you're allowed to is fantastic. It makes every question much easier, almost all the time. Okay, what fraction of integers in between these things are cubes? Now there are 8,000 numbers here. And we're looking for cubes over total numbers as a fraction. So how many cubes are there up to 8,000? Well, if you want to, you can start working out some cubes. 2 times 2 times 0 is 8, 27, 64. Now this is going to get more and more annoying. And actually, it's hard to know exactly how far you're going to have to go, and it's going to get very painful. I think what you're supposed to do here is notice what I noticed when I wrote down this one, which is if 2 cubed is 8, well, I'm looking to go up to 8,000. This means that 20 cubed, which is 20 times 20 times 20, well, 2 times 2 times 2 is 8, as we've said, with 3 zeros on the end is 8,000. So 20 cubed is the highest cube we can go to. All cubes lower than that will be lower than this, and all cubes higher will be higher. So there must be 20 cubes up to this. And so the answer is 20 over 8,000. Cross off the zeros, divide by 2, and we get 1 over 400 as our answer. 19. I mean, this is just a Sudoku. So if you haven't played much Sudoku, you're going to be in trouble. If you have played quite a lot of Sudoku like I have, this wasn't much of a challenge. I would recommend trying it. It's a good game. I mean, you can play as much of this particular Sudoku as you want, fill in as much as you want. I'm just going to do it the quickest and most efficient way, which is just notice, and by the way, this isn't what I noticed right away, I'm just doing it for the video. Notice this column here, and just think, where is the 2 going to go? The 2 can't go in this box because it's being shadowed by this 2, and it can't go in either of these 2 boxes because this box already has a 2. So in this column here, 2 can't go here or here, which means 2 must be there. So x must be 2. And that's the most efficient way of doing that question. Question 19. Emily writes down the largest 2-digit prime. They're obsessed with 2-digit primes in this test here, such that each of its digits is prime. Okay, so the prime numbers or prime digits are 2, 3, 5, 7. So she's writing a 2-digit prime that's made exclusively of these numbers here. Okay, so the largest one is going to start with a 7, clearly, because we've discussed before, largest numbers need biggest digits first. So 77 doesn't work, that's 7 times 11. 75 doesn't work because it ends in a 5. 73, I think 73 is prime, so 73 is probably the largest one I can do here. This other person writes the smallest one that you can do with this. Well, again, start with the smallest number this time. 22 isn't prime, but 23 I think is. And the difference between these numbers is 50, which is going to be the answer. 21. So, if you're not so hot on interior angles of polygons, maybe watch a video about it. You can just YouTube interior angles of polygons. There's a couple of videos on this channel that talks about them. I happen to know the interior angle of a regular hexagon is 120, and honestly, if you're thinking about taking question 21 seriously, you should probably also just know the first kind of 6 or 7, maybe not the 7th because that's annoying, but the first 6 polygons, probably just know the interior angles for. Of course, this also helps with triangles, which is just a polygon that has interior angle of 60, which I think most people probably do know, and of course squares interior angles of 90. So actually all I'm asking you to do is memorize that pentagons are 108 and hexagons are 120. I think if you just knew that, it will just save you a lot of time. Otherwise, watch this video and learn. So these are all the things that they've given us here. And are we told anything else? So not really, but we're told that this is a regular hexagon, of course, which means this length is the same as this length. I've also said this is 30 because the whole angle is 120, and so 120 take away 90 is 30. Okay, this length is the same as this length, which is also the same as this length because this is a square, and squares have all the same sides. But that makes this an isosceles triangle, so 180 take away 30 is 150, divided by 2 because these two angles must be the same, so they must share that 150 is 75 and 75, and then we're looking for XVR, which is this angle. So 360, take away those 3. You'll eventually get your answer when you do a column subtraction or whatever of 135. Quite a nice question. I think we're going to there's only a few questions left, and if I remember correctly, they're all quite difficult, I thought. So okay, let's look at this multiplication then. Now we've got a 4-digit number multiplying by 9 to make a 4-digit number. Now that means that this number here, this number can't be a 2. Because when you get to the end of the multiplication, 2 times 9 is 18. And you would put an 8 here, you'd add whatever leftovers you had, but then you'd have to put another digit here, that carryover, because you've got a 2-digit number. So because you're not doing that, t can't be anything bigger than 0 or 1, right? Because 0 times 9 will give you a 0, and you just take the carryover from here. and 1 times 9 is 9, and then actually that would force you to have no carry anyway. But okay, so those are our choices. T is 0 or T is 1. Now, let's just think about this a bit logically. If T is 0, then that means that this is 0. Now, we're thinking about the value of r. R could actually be anything in that case. If T was 0, because r could be all the way up to 9, 9 times 9 would be 81, and then you just carry it over and you'd be fine. So r could be any number. But if T was 1, you'd do 1 times 9 is 9, and then you couldn't have any carry here. So then you're in the same situation as I just talked about, where if there's no carry going to the next number, then what you must have multiplied must be, again, 0 or 1. Now, T can't be 0 and R 0 because they're apparently all different digits. Sorry, this is in the case where T is 1. So T can't be 1 and R is 1. So if T was 1, R would have to be 0. But I'll get to that in a second. First, let's discuss this case if T was 0. R could be any number, but actually let's replace these with zeros now and think about the start of it. P times 9 ends in a 0. Now that either means that that doesn't either mean anything. That means that P is 0. The only way to multiply by 9 to get 0 is using 0 or 10 or whatever, but it can't be 10, right? It's a one-digit number. So P must be 0, but we've already said T is 0. So this case just fails, right? Because we're using the same digit. They must all be different digits. So T can't be 0. So T has to be 1. And if T is 1, R can't be 1, because then again, different digits. So R has to be 0. And that'll be our answer. R has to be 0. Again, just thinking really just about the carry on or the carryover when you do one of these multiplications, but that must be the answer there. You can verify what the rest of it will look like in your own time if you want to. But yeah, okay. 23. So we're looking for this shaded area here. This is quite a nice question. We've got squares side 6 and 6 and square side 4 and 4. This is the midpoint K. So this side down here is 2, which of course makes this 2. And now there's probably a few ways you can do this. I thought what I did was probably the easiest, but not the easiest thing to see. But it is the easiest in terms of its maths. This length here must also be 2, which means that this length here is 4, because 4 plus this 2 will get us this side 6. And now this side is also, of course, 4, because this is a square, which means I can actually just fill in, because this is a right angle down here, a sort of another square here of side 4 and 4. And now this entire triangle is just going to have area of a half times 10 times 8. Half base times height. Base being 10, height being 8. Now, of course, a half times 10 is 5 times 8 is 40. But here, now I have the area of this entire kind of fake triangle. I can just take away what I made up. Now, of course, 4 times 4 is 16, so I just need to take away 16, and I get the shaded area as 24. Now, I think I just thought of that because I've seen problems a bit like this before in other math challenges, but that's a lesson in itself, right? Just do lots of math challenges, prepare yourself well, practice lots of stuff, and you might be able to see this kind of thing as well and do it that way. There are probably lots of other ways to do it though as well. Last couple of questions. I did not do this in a very nice way, I don't think, but it was the only way that I did see how to do it. So, okay. I said, well, if this angle is P, so is this angle here? Of course, this is a regular heptagon, so all these sides are the same. So I said this whole angle here is P, which means Q is 180 minus P, based on angles on a straight line. Like if P was 120, Q would be 180 minus 120 for 60. Okay, so Q is 180 minus P, but also exactly the same thing over here, right? Because, in fact, that should say a T. I don't know how I've managed to get that so wrong, but we're so late in the video that I'm not going to change it. Spoilers for everything else that's going to happen in this question here. There's a lot of stuff on the screen. But anyway, that should say T, right? T is 180 minus P, for the same reason as Q is 180 minus P. Now, this angle is also P in here, because again, it's just the interior angle of the heptagon. This angle here is S in here, because this is an isosceles triangle. So P plus S is 180, looking at this small triangle. Which means 2S plus P is 180, take away P from both sides, divide by 2, and we get this statement for S. And I can make exactly the same statement about R, just doing exactly the same working in this triangle here. And now, instead of expressing this as a load of different letters, I'm going to express it all in terms of P, because I have all of these letters now. I have all of them in terms of P. So I'm going to say P plus Q, which I know is this, plus R, which I know is this, plus S, which I know is this, and I'll have a statement with a bunch of P's in it. So, okay, we're sorting this out. 180 plus 180 is 360. P minus P is nothing, minus another P is minus P. So just putting those three things together, I get these two. And then putting these two together, 90 plus 90 is 180, minus 2 halves is minus 1P. And I end up with this. Now this isn't the answer because it's none of the answers on the screen here, but they do have Q's in them. So what I'm going to do is I'm going to go back to my statement with Q. I'm going to add P to both sides, take away Q from both sides, and then take this thing for P that I have here and put it in here instead. And then expand out. Minus minus makes a plus. Just be very careful of. And you eventually end up with 180 plus 2Q. I think there's probably easier ways of doing that, but I mean, I'm someone who's very confident with their algebra, and this is question 24, so I'm hoping if you're still watching you are too. So that is one way of doing it, I guess. 25, a much more pleasant question, I thought, though maybe other people would disagree because I didn't like it when I first saw it. Okay, so you're adding up the edges of this triangle. So let's do that first. Let's add up this edge, and that gives us this. This edge added up is this, and this edge added up is this. And apparently, we want all of these sums, these edge sums, to be the same number. And not only that, but it's asking us what's the largest that's possible to make that number once you have it all the same. So okay, what I thought about this question was, let's first just make all these numbers the same. Let's kind of fix this such that the numbers sort of become the same. And actually, while I'm there, let's aim for one of these things, because I may as well. So I decided to aim for 48, since it's in the middle. So I'm going to aim for 48. So okay, well I need this one to be increased by 8. So I thought, if I just swap the 5 and the 13, I'll increase this side by 8, because this is 8 bigger than that. So this will be a 48. This side will go up a bit too big, but that's okay, because it's increased by 8 as well. But now I'm sort of closer to this. I need to make this one smaller by 3, and this one bigger by 3. And then I noticed that if I just swap these two numbers here, I can achieve that. Because if I swap the 12 and the 9, this side gets smaller by 3, but this one gets bigger by 3. So swapping the 12 and the 9, I can make them all 48. Okay, so that's my first objective done. I found a triangle that does this thing, and it's one of the answers. So now all I need to do is figure out, can I do bigger? Can I also swap some numbers around to get them all 52, or even all 54? Okay, so I thought of a couple of things here. Firstly, if you want to make these numbers as big as possible, I think I need to make the 3 numbers in the corner as big as possible, because they're the numbers that are being shared and are part of 2 different sums. So I think in the corners, if I want to go as big as possible, I think the corners need to be 13, 14, and 15. So I thought, okay, let's swap the 14 and the 11 then. Let's make the corners as big as possible. Now that, of course, changes my sums a little bit, but that's okay, because I'm aiming to get up to 52 as a minimum, so that's fine. I've got all the biggest numbers in the corners now. The other thing I thought was, okay, again, if you're trying to go as big as possible on these, you want to make these 3 numbers in here as small as possible, because they're not even contributing to the sum, are they? To any of the sums. So I need to make these numbers 1, 2, and 3. Now I've already got the 2 here, that's fine. So let's swap the 5 and the 1 to put the 1 in the middle. So I've just swapped the 5 and the 1 right now. That puts the 1 in the middle. And I've also swapped the 8 and the 3, actually. I did both at one time. So that gives me the biggest numbers in the corners, which are being used twice, and the smallest numbers in the middle, which aren't being used at all. And actually, I'm very close to a solution. This side is just off a little bit, but that's okay, because I can see if I just swap the 6 and the 7, I'll end up with reducing this side by 1 and increasing this side by 1. So that'll give me 52, 52, 52. So again, I have another solution now. It's 52. I just need to think, can I get to 54? And again, I think because of the things that I've done, I don't think I can. I've put the smallest numbers that aren't going to be used in the middle, and I've put the biggest numbers that are going to be used on 2 edges on the corners. So I don't think there's any way I can get bigger than 52. And I'm fairly happy with that logic, so I'm just going to say the biggest must be 52. And that's the whole paper. I thought some of it was quite difficult, but really well done for watching and preparing yourself well for the challenge. And yeah, see you next time.